Welcome. In this session, we'll explore the directional derivative. Here's our motivation. Suppose that we're given a function that takes a two-dimensional vector and maps it to a real number. And we could write that functionally as a function that has a vector argument. So the question is, what is the rate of change, right? So if we're given a vector, let's use this functional term, if we give it a point in 2D space, we can compute a real number. From calculus, so from, let's say, from prerequisites, we know how to calculate prerequisites. We know that the rate of change for, let's say, vector entry j, that is the partial derivative of the function with respect to that jth variable. So we want to know what is the rate of change in a general direction. Well, let's take this in pieces. Let's start by consider the elementary vector. And an elementary vector is often written using the symbol E, and it's a vector, and then the jth one is a vector that is all zeros except that the jth entry is 1. So in a two-dimensional space, we have elementary vector 1 simply equals 1, 0, and elementary vector 2 simply equals 0, 1. That's relatively easy. If we want to, we could even say it is defined as. So now, for these elementary vectors, what is this? What if we take the limit as a scalar value goes to 0 of, suppose we take our function and we take the argument plus this amount h times elementary vector j, we subtract the level at the argument, and we divide that by h. So what does this do? Well, let's suppose that we're looking at elementary vector 1. What that will do is this term will add h to w1, and it will add 0 to w2. And that means that this will have the effect of giving us the partial derivative of the function with respect to the first variable. Likewise, if we use elementary vector 2, then this will add 0 to the w1 entry. It will add h times 1 is h to the w2 entry, and that will give us the partial derivative of the function with respect to variable 2. Now, of course, what we're actually doing is we're sort of slipping in between variables and vector entries. So let's say that what we'll do is, because this acts the same way as the partial derivative does, let's say that we will define this to be giving us the partial derivative of f with respect to entry j at an argument. That is, we have reasoned that if this was a multivariate function, that it would be giving us those partial derivatives. So we'll say, well, we will define the partial derivative of a vector entry as being this limit. So that's a powerful idea. When we have that, what we can do is we can prove that we can, so this is a fact. A fact to me is a theorem that I'm not going to prove because we can find the proof somewhere else, and you can find this proof in multivariate calculus texts. We can prove that the partial derivative of the function with respect to entry 1 of the vector times entry 1 of v plus the partial of f with respect to entry 2 of the w vector times entry 2 of v plus, and if we continue on, that is the plus the partial derivative of f until we get to the nth vector of the nth entry of the w vector times the nth entry of v, well, that equals a summation, and that equals the result that we had in the previous session. That is a one form. So we could put this as a one form, the partial of f with respect to 1, the partial of f with respect to 2, and so on until we get to the partial of f with respect to n, and then it is simply times v. We come across this so often, we will write this as the derivative in the direction v of the function evaluated at argument w. So this is the directional derivative. And this now lets us write, now we can write this very concisely. So if we want to say what's the derivative of a function that has a vector argument in a direction, we can write d sub vector v, and that captures it. And when we want to do the computation of the directional derivative, we have this. So what this does is, let's observe that this is a scalar value. So what this is saying is that if we're at some point in a vector space w, and we have a scalar function of it, f, that the derivative in a direction is the result of this computation. So let's suppose that we have a 2D example. So this is W1, this is W2, and if we're at some place, W, and we have some direction that we're interested in, we can find the directional derivative. Because it's this one form times a vector, it's a very simple computation. What you can do is you can think of it as saying, oh, the directional derivative is a weighted sum, that we're going to take the partial derivative of the function in direction w1, and we're going to weight that by the amount in v. Then we're going to add the partial derivative of f in the second direction, and we're going to weight that by v. So there are many ways that you can think of, and the exact way that you think of it and the exact interpretation you have will depend, of course, upon you and how you think, and it'll also depend on the problem that you're trying to solve. So what we'll do is we'll actually take this expression and we will make a definition. So we will define, we'll say the directional derivative in direction f of a function at an argument value equals, by definition, so this is the definition, is it's the limit as a scalar value approaches 0 of, we take the function and its argument, we add an infinitesimally small scalar multiple of v to that, we subtract the level of the function at the argument, and we divide that by this infinitesimally small a. So let's observe in passing that some authors will require that this vector v have a unit length. That is, some sources will require that the norm of the vector equals 1. And we won't make that restriction. What we do have to have is an important thing, is that we will require simply that that vector v is not the zero vector, because the directional derivative in direction of magnitude 0 simply doesn't make semantic sense.